Alright, so we have our first example of an assembly line balancing problem over here. So given to us in this question, uh, a team have been given a task to produce 120 units and they have been given a total production time per day of 10 hours. Okay, then we can see the tasks that they are to perform to produce any of the units over there. So from A to H, task names given over here. Then the time allocated to each of the tasks in minutes. Then we have the precedence over here. Now this has to do with how the tasks are arranged, okay, in that successive order. So which task comes before which task, right? So in that order, that has to do with the precedence over here. So, so we have task A, which doesn't follow any task. That is why we have this hyphen over here. Now B following A, that means if task A has not been done, then we can't do task B. Then task C also following task A, then D following B, E following both B and C. Okay, so in order for E to occur, B and C has to be completed. So we have to finish with these two tasks before we can do E. So in that order, so we get to H, okay, where chain has to be performed before we can perform H. Very, very important. So we have the task table time over here. Then we have been told to draw the precedence diagram containing circles and arrows. Then determine the cycle time, the theoretical number of workstations, assign tasks to the workstations, and find the efficiency of the balance. All right, so let's move on. Okay, so we have our precedence diagram over here, neatly drawn. So we can see from the beginning we have A. So from the task timetable, we noted over there that A didn't follow any particular task. Okay, so A was the first task, then followed by B and C, which both followed A. Okay, so we can see that over here. So we have B and C following task A. All right. Then we have task D, which follows task B. So let's check that. So we have task D, which is following task what? B. Then we have task E, which follows B and C. So as we can see where E is positioned, an arrow moving from B to E and moving from C towards E over here neatly. Then we have task F, which follows task D. So you can see over here we have F, which follows D. Okay. All right. So F following D. Then we also have task G over here. Now it says that task G follows C, E, and F. That means all these three tasks has to be done before G can be done. Okay, so we can see that an arrow moving from F to G, from E to G, and from C to G. Then we have the last task, which is H, which follows task G. All right, so very, very simple. Right, so we have the precedence diagram over here. Then let's move on. Then how do we determine the workstation cycle time? So in order to do that, first we need to convert the hours given to us to minutes. So just multiply it by 60. So you multiply the 10 hours by 60, then you get everything in minutes, having 600 minutes. Then we also given to us in the question was the required output per day, which was 120 units. So divide this time by the required output per day, giving us 5 minutes as the workstation cycle time. Okay, let's move on. Then we also need to find the theoretical minimum number of workstations that can satisfy this workstation cycle time constraint. Okay, let's move on. So first of all, we need to find the sum of all the tasks. So just add the time allocated to each of the tasks then you get 21 minutes. Now divide that time by the number of divide that time by the workstation cycle time. Okay, then after dividing you get 4.2. Like we said, when you get a decimal, run it up to the highest, the next highest integer. So we can't say you have 4.2 workstations. It's not practical. So we run it up and we get 5 workstations. It doesn't mean that this is the number of workstations that can satisfy uh, the workstation cycle time constraint. Okay, it might be more than that. So that is why we also call it theoretical. Let's move on. Then we need to assign the tasks to the workstations. So we first come up with a primary rule, and the rule chosen for this case was assign tasks in order of most following tasks. Okay, so all you need to do is count the number of tasks that follow each task. As simple as that. So we have a table over here indicating the tasks and the number of following tasks. So it says that A has 7 tasks following it. So let's move on quickly and find out if that is true. So we have A over here. All these tasks follows A. Okay, so if A is not done, any of this, none of these tasks can be done. So let's count 1, 2, 3, 4, 5, 6, 7. Okay, so A has 7 tasks following. Then B has 5. Let's find out. So B over here, 1, 2, 3, 4, 5. 5 tasks following. Then it says that both C and D has 3 tasks. So this is D. Let's count. 1, 2, 3. Then we also have C over here having 1, 2, 3. Okay. So don't count it this way. 1, then come and count 2, then you say that it moves from this side to this side, making 3. No, we just counting the tasks, not the movement. So C is also 1, 2, 3. D is also 1, 2, 3. Okay, so we can see that in this case we have a tie. Both have 3. So wait, then we move on. E and F. So F has 1, 2. E also has 1, 2. Another tie. Then G has one task following it, which is H. H doesn't have any task following it. So in that order, nicely over here using the primary rule. So we need to come up with a secondary rule that breaks these two ties over here. So we do that over here. Right. So the secondary rule says that assign tasks in order of tasks, largest task time, precedence diagram, and the task time. That means we use this one. If this is not able to break the tie, we move on to the precedence diagram. If it's not able, then move on to the task time table. Okay, so we have a table here where we have the workstations. So you can see that the total number of workstations used was 5, which matched the theoretical number of workstations. All right, but in some cases, like I said, it might not be the same. So we have them. We'll go through this table quickly. All right, so let's move on to the first task, okay, which we had to be task A. All right, so we assign task A. Since there was no tie, we assign task A to workstation 1, which is the first workstation. And task A needs 4 minutes, okay, to be completed. Right. But we know that the workstation cycle time is 5 minutes. So since task A needs 4 minutes, when we subtract the 4 minutes from the 5 minutes, we'll have 1 minute remaining, right? Then we ask ourselves the next task to be performed. Can we complete the next task in the 1 minute? It's not possible because task B is the next task. It requires 2 minutes and the time remaining is 1 minute. So since we can't complete task B in 1 minute, then this 1 minute now becomes an idle time. Excuse me. The 1 minute becomes an idle time. Okay. Right. So what did we do? We assigned task A to workstation 1, then subtract the time taken to complete task A from the workstation cycle time. You will have a remainder of 1. Now ask yourself, the remaining time, can it complete the task, can it complete the next task? If not, then it becomes an idle time. That is why I have idle beside this 1 minute over here. Okay, so that means that it is only task A that can be performed in workstation 1 based on the workstation cycle time constraint. Only task A can be performed in workstation 1. There will be an idle time of 1 minute over there. Let's move on to the next workstation. Now, workstation 2. So, task B assigned to workstation 2. And task B requires only 2 minutes to be completed. Subtract the 2 minutes from the workstation cycle time, 3 minutes remaining. Okay, now let's move on. Now we notice that we had a tie between C and D, and the secondary rule says that we should find out which of the tasks has the most largest time. So let's move on to the task timetable. As we can see, C and D both have 1 minute. Okay, so that rule cannot break the tie. So the next one says that, okay, if that doesn't break the tie, then move on to the precedence diagram. Let's find out from the precedence diagram, C and D. So we can see that on the precedence diagram, C comes before D, right? So I'm using the number of tasks that occurs before that particular task. So with C, only A has to occur, but with D, A and B has to occur. So C takes precedence in this case. Okay, so C is performed, right? Now, since we only require 1 minute to perform task C, so task C can also be performed in the same workstation, which is workstation 2. We don't assign it to 3. The remaining time is more than the time required to perform task C. So it is also assigned to the same workstation, which is workstation 2. Then this time around, we don't deduct 1 from 5, but instead we deduct it from the remaining time, which is 3. So we'll have a remaining time of 2 minutes. Then since D also requires just 1 minute, we can also perform that task also in workstation 2. Okay, so we perform B, we perform C, then we perform D, right? Then we'll have an idle time of 1 minute. Okay, since the next task has the time allocated to the next task is more than 1 minute. Okay, right. So we come up, so the next workstation follows, which is workstation 3. Then we had a tie also in this case between E and F, and it says that we should use the largest task time. So let's find out between E and F who has the largest task time, which is E, 5 minutes. Okay, so E comes first with its 5 minutes task time. Now subtract the 5 minutes from the workstation cycle time, you get 0 because that is also 5 minutes, giving you 0 over here. Then move on to the next workstation. F is assigned to that workstation. Now F has a task time of 3 minutes. Subtract it from the workstation cycle time, which is 5 minutes. You have 2 minutes remaining. Now, since the next task, which is G, the task time allocated to that task is more than 2 minutes, the 2 minutes over here becomes an idle time, right? So we assign G not to workstation 4 because the time remaining is small. Okay, it's less than the 4 minutes. So we assign it to a new workstation, which is workstation 5. So G is assigned to workstation 5. Then we'll have a remaining time of 1 minute, and H only requires 1 minute to complete the task. So H also follows in workstation 5. So having a remaining time of 0. Okay, so that is how the tasks are assigned to the workstations. Very, very simple. You just need to obey the primary and secondary rules. Right. Now we can compute the total idle time we are having, which is 4 minutes. Okay. Now let's move on and let's find the efficiency of the balance that we have over here. Is it worth it? If it is not worth it, then we need to go and come up with new primary and secondary rules in assigning our tasks. Remember, you can't go in there and say that I want to subdivide my tasks because my efficiency was low. We said that the tasks cannot be subdivided. In your attempt to do that, you might end up even reducing your efficiency. Okay, right. So you need to check your rules that you use to allocate the tasks to each of the workstations if your efficiency is not satisfactory. So first, let's find the efficiency before we can move on to that. Okay, so let's find the efficiency, which says that we need the sum of the tasks, then divide it by the actual number of workstations, then multiply that of the actual number of workstations by the workstation cycle time and divide it. Okay, so that is what you need. So sum of the sum of the task time divided by the actual number of workstations times the workstation cycle time, then you multiply it by 100. So after dividing this, we got 0.84 multiplied by 100, we got 84%, a significant one. So we are going to stick with this balance, stick with our primary and secondary rules because our efficiency is satisfactory. Thank you, and we'll look at another example in the next lecture.